Hello, welcome to the presentation for my final project in Applied Deep Learning. As you can see, I chose a medical imaging project that Professor Gordon proposed to us. First, here's a short overview of my presentation. I will give you a short introduction to this project, and then I will talk about how I pre-processed the input before training the models. Finally, I will talk about the different models I used and how I evaluated them. I will then conclude with recommendations for future work. The task we're trying to do in this project is to detect cancerous cells in biopsy images. The regular process to do so is shown on this figure. First, tissue is extracted from the human body. That can be, in this case, from the breast, because this is for breast cancer. But it could also be, for example, for the brain, if we would want to look at brain tumors. The tissue is then analyzed under the microscope by a doctor, who then makes a diagnosis using these kinds of slides. That's what they see underneath the microscope, and this is what we're going to use in our project. Our goal of this project is to assist the doctor who makes these diagnoses. So we want to have a second automated opinion for the doctor, which can also tell him whether that second automated opinion thinks there's cancer on the biopsy image or not. So for example, if the doctor would say, I don't think there are any cancerous cells in this image, but then the automated second opinion would say, actually, I think I do, then the doctor could use a second pathologist to then get another input from another person to then be more sure about the evaluation of the image. It is important to say here that we aim to assist the human pathologist, not to replace him. So this is all just going to be a second opinion. This model is nowhere close to being able to actually just do the work all on their own. We want to develop this model. We want to develop a model that takes these biopsy images in, just like the doctor takes them in through their eyes, and then as an output produces a heat map. So as we can see here, we have a raw image. We are going to take a mask, which in this case is the ground truth, but in case of our model would be a mask model generated. And then we would overlay that over the raw image and would get a heat map out of that. And that heat map would then show us which parts of the original slides the model would classify as cancerous or not cancerous. And as inputs, we're going to use these raw images, which are collected in a larger data set used for the Chameleon 16 challenge. There's actually 400 slide images of those, which all come at different zoom levels, and they were independently collected from two Dutch medical centers. This is also what Professor Gordon has provided for us. We know the label of each of these because they have all been annotated by these kinds of masks. They all have annotated masks like this, which have been made by pathologists. So it's not just been a single pathologist who's done this, but actually a group of pathologists who then all agreed on a mask.
So yeah, to accomplish this task, I first set out a process with full slide images to be able to train a model. I then put a few of them into a training validation set and a few of them into a separate test set. So if we look into that really quick into the notebook I submitted, we have my project here. This is just general setup stuff like all the input statements, etc. And then here we go where I download and create those files. So these are the slide paths specified. I then download them in here. And then they are all stored in a dictionary of var slides from mask, where I then later retrieve them to get the separate patches. And then yes, talking about the patches, so I used the patch-based approach that was outlined in the main paper and also suggested by Professor Gordon. I used the zoom level of 40 alone, as well as the free zoom levels during training. So what that means is that I took a slide image, I randomly sampled the center on that image, and then I created 3 different patches, all centered on, let's say, 128 by 128 center. So we had just like the most zoom in patch, and then we had them going further out. And then I used both just the single version where I just used this 40 patch, as well as a version where I used all of the different zoom levels to train the models and to then make a prediction of them. So if we go further in the input pipeline here, oh, I forgot that. That's like where I create the test set, which is just the same as before. And we have the zoom level set here. I have to say here, I tried using higher zoom levels, but it just didn't work. So Colab would always just crash and tell me I'm using too much RAM. Like even now, I'm not using anything for some reason. It's like loaded up. And so I tried using anything like 3 and below because we were supposed to use the lower zoom levels, but it just wouldn't work. Even for 1 or 2 slides, Colab would just crash as soon as I would try to get the training data and the labels. And so at one point, I just settled and said, okay, I guess I'm just going to use 4. And then for some coding training purposes in the beginning, like I set it up with 7, and then like when I got more in depth into it and the entire structure was built, then I switched to 4. And yeah, so I had the patches around the center, so this is what's happening in here. So we have a function here called sample window, which just randomly samples one center. Not one center. You give it an amount of patches it has to get. You give it a specific slide and a specific mask. And then it goes through the specific slide and the specific mask and randomly creates centers until it has reached the amount of patches you want to have. And then it also checks, as soon as it has found a center, it checks if there is tissue around in that patch around that central region. So the first thing it checks is there even any tissue in the center I'm looking at. If there isn't, then it just immediately discards the center and creates a new random one. And then in case there is tissue, that goes in and it then tries to label the mask. So the patch it retrieved. So what it does is looks at the mask which is provided in the data, and then it retrieves the label from that mask. So it looks, is there at the center, is there cancer cells or aren't there? If there are, it labels it with 1, if there aren't, it labels it with 0. And then it goes inside, and then it checks, okay, actually for all the different patch sizes what I have to do, so for all these 3 different zoom levels, they all come with different sizes, I'm gonna extract the patch, which is centered around the center, and then I'm gonna store it in this kind of collection. And what it does also for the larger ones, it always downsamples them to 299 by 299, so also as is described here, so that we always have the same input to the model, a same input size. And then it stores them in this data structure, and it then, in the end, appends that data structure to the larger collection of all the different patches it has collected for all the different center regions, and then at the end it just returns however many patches we originally set out to get. So this is defined in here. For the next step, I then used image data generator both for data augmentation and for the training validation split. So the first part we have is a training validation split, where I split it into 80% training, 20% validation, and I also shuffled the labels and patches together before doing the split, so that the validation set would actually consist of all the different slides. So what I realized is that image data generator just automatically takes the last 20%, and the entire data set is for validation, and it doesn't actually shuffle them. So what happened was that the validation set would usually contain patches from only 1 or 2 slides, whereas maybe in total the training set had like more than 1 or 2 slides, obviously. And so in order to avoid that, I shuffled them before, but I shuffled them so that the labels and patches are still in the same indices, and the validation set is just later. So we can see that if we're going on here, the create data and training and validation set section. This is just some conversion stuff, and then here I'm shuffling them in unison, and then here right now the 2 different other zoom levels are deactivated because I later didn't use them anymore, as I will explain later. But I shuffle them in here, and then I feed them into data image generator, just how we also did it in our homeworks. And I apply different data augmentations to them, so I apply a 90-degree rotation range to them, I apply 2 flips to them, and I decided to use these data augmentations because it worked well with my training set, so I got better results with them, and the main paper also recommends them. And as the main paper also says, it's valid to actually do all of these data augmentations in the training set, and it won't screw any data. And then I also thought about doing the color data augmentation, but it just started taking too much RAM, and so I just kept it to these geometric augmentations. And just to give you a quick overview, so because I talked about a bunch of different stuff I just did, so right now I just talked about training. So I described how I randomly sampled the center region. So if I have the entire slide here, I would just randomly extract sample centers all over, and then I would create the different zoom levels. So I would create patches for all the different zoom levels. And then I would apply that augmentation to them. So I would rotate them and I would flip them both horizontally and vertically. And then once that would be all done, then I would feed them into the model for training purposes. So I obviously didn't do the same thing during inference. So during inference, I actually wanted to just have that slide and actually create this heat map, which I talked about earlier. So I actually wanted, like we see here, I have this draw image slide. I wanted to create a mask like this and then actually put a heat map over it. So I couldn't randomly sample them anymore. So what I did instead is I had a sliding window which just kept sliding over these. And then for every single center region it would extract, it would then let the model predict is it cancerous or is it not. So the next step then was to develop different kinds of models. I started using transfer learning, just like suggested with the Inception v3 model, and then I also tried to build a custom one and also tried to use the actually pre-built model, the Inception v3 one, to actually do a more complicated setup. Before I dive into the models, let me show you really quick where you can find them in the code. So I have this build model section here, so just also here you have like this overview and there's build models right here. And then we have these 4 different models that I built. My own model actually just is the custom convolutional model. I just accidentally didn't rename it yet. Okay, the first type of model was the Inception v3 model, which I actually just got via transfer learning. So as you can see here, I just specify the input shape I have, which is actually just the default shape. I load the model, just as a base model, then I put another averaging layer on top of it, and then my own top layer of the prediction layer on it, which then predicts the two different classes. I froze the entire model just because at first I really just wanted to train the top layer, and that was it, and see how well it performs. And then otherwise I used weights from ImageNet, as you can see here. And I compiled the model. I also added early stopping to it, just because I found that sometimes it would start training very well over 10 epochs, sometimes it would be already at its peak after 4 or 3. So I added early stopping to that to then just save myself some computing time, and actually then I'm also to be able to restore the weights to actually the best epoch, so wherever it has the best validation accuracy. I used this model first off the shelf, just with one zoom level, the maximum one. So if we go back here, you can see I just used it with like the regular patches around the center region, no downsample patches. And it performed quite well, so I got a validation accuracy of 75.56. We can see here that although it fluctuates, like in general, the model accuracy went a bit up. And then here we can also see that the model loss in general just went down, and the test loss is further down the train loss, which is good, because that means it's not overfitting. At the same time, though, if we would look like another 1-2 epochs ahead, it actually would start overfitting, and that's where the early stopping comes into play, and that's why it's not shown here. So I then took this off-the-shelf Inception v3 model, and I tried the multi-scale approach. So as was outlined in the paper, when actual pathologists look at these biopsy images from a microscope, they zoom in and they zoom out. And to kind of model that kind of behavior of both taking context as well as detail into account when making a decision, I just extracted patches for 3 different zoom levels, all separately, and then I trained 3 separate Inception models on that. I had a problem here, however, that because Colab kept crashing because of RAM, I could barely use any good zoom levels. So anything lower than 6 would cause Colab to crash, and 6 is a really, really like low resolution zoom level. So I didn't really have high quality training patches there. And then even when I used this really high zoom level, I still couldn't extract many patches per slide. So the training set here really wasn't good, which is how I think these very low accuracies for every single separate model during training happened. And I then had them vote on the test set heat maps, and I'm also going to talk about it later in the evaluation section, but they basically just all voted 0 all the time together. And so that wasn't a very successful model, and that's why I didn't really further went down that path. I then figured maybe instead I might use just a non-pre-trained model. So as you can see here, the model base in here is frozen. But here then I unfroze it and just completely trained it from scratch just to see what happens and maybe if I can optimize it in some way. And I also trained it only with 1 zoom level because the multi-scale zoom level approach really didn't seem to work out with the RAM and GPU I had available. I achieved the validation accuracy here only of 58.89%, which was like the best one. And as you can see here, the model didn't really train much. So like the accuracy basically stayed the same and then it just went down once. And then similarly for here, yeah, the loss goes down at the beginning, but then it kind of stays the same and it just fluctuated a bit. I then went on to do a 4th model, which was just completely from scratch, a custom one, just because I was curious how well would it perform compared to, for example, the Inception v3 model. I also thought maybe I could implement the multi-scale model with it, but already on 1 zoom level, it had again this really low accuracy, just of 58% again, and it also didn't really train much, just like the one I had before, where I also trained Inception v3 from scratch. So I just decided to also not further pursue that way. And I instead focused some more time again on evaluating Inception v3 and just building my evaluation methods. And then just to show you really quick, so again, here you have Inception v3 using transfer learning, and then you can open it up and then you can see how the base of the model is defined, and then how I trained it, and then here's just a plot which is still included in the output here. And that's the same for all of the other 3 models as well. So you can click it on the notebook there. And then continued on to evaluate each model using a test set of 6 slides. I generate heat maps for each of these 6 slides